Hello, in today's video we're going to be talking about graphing quadratic functions. In Chapter 7 we talked all about factoring quadratics, so now we're going to move on into graphing them. There are a few different forms that we're going to be looking at. The first form that we're going to be focusing mostly on today is f of x is a times x squared, which means we've got something like f of x or y equals a number, maybe 3, times x squared. And we are going to take that and graph it in a coordinate plane. So far we have talked about graphing linear equations in the form y equals mx plus b. And we did that by identifying your y-intercept and identifying your slope and drawing the line. This line represents all possible solutions to your equation. So this line represents every single x-y pair that I can plug in for x and y in my equation, and it will be true. So similarly, we're going to do that same thing with quadratics. So 8.1, graphing f of x equals a times x squared. Our essential question for today is, what are some of the characteristics of the graph of a quadratic function in the form f of x equals ax squared? Our f of x equals x squared is what we call the parent function, meaning that there is no multiplication or addition or subtraction causing us to change our just normal graph of x squared. So we're going to go ahead and see what this parent function looks like. The parent function specifically is only this one example. Later in our notes you're going to see we're multiplying our x squared by a certain value. So we are going to be changing our parent function. So I'm going to go ahead and make a chart. I'm going to start by putting in an x value. Here I'll compute f of x is equal to x squared, and then I will have my y value. So I think it's good to start at the origin and then maybe take two numbers below and two numbers above. So if I put in a -2, f of -2 is -2 squared, which means that I get a +4. Plugging in a -1, f of -1 is a -1 squared, which means I get a +1. f of 0 is 0 squared, which means I get 0. Plugging in a +1. Now since we're squaring, 1 squared is the same as -1 squared, so I get +1 again. Plugging in a +2, again since I'm squaring, a +2 is the same as a -2 squared, so I get +4. Drawing my graph, I've got the point -2, 4, so I have a point here on my graph. -1, 1, 0, 0, 1, 1, 2, 4, and so my graph looks something like this. When I connect these dots, it's going to look almost like a U-shaped graph. We call this graph a parabola. Anytime we graph something that has x to the second power in it, you are going to see this U-shaped graph show up. So what we're going to be doing as we move on in our notes is we are going to be changing the numbers in our equation, but you will still see x squared, which means that your graph is still going to take this shape in one way or another. So for example 1, I'm going to create a chart, find some points, and then graph this equation. I know that it is going to have the shape of a parabola because I do see that x squared in there. So I've got x, I've got y equals -x squared, and then I have my y values. So again, I'm going to go ahead and put in 0 as the middle. I'll go -1, -2 again. We could go to 3 if you're interested in finding more points. -x squared, so y is -2 squared. -2 squared is 4, but then we make that negative, so -4. Here I've got negative of -1 squared. Negative 1 squared is 1, but then I make it negative, so I get negative 1. Negative 0 squared. 0 squared is 0, and negative 0 is still 0. Negative of 1 squared. 1 squared is 1, make it negative. Negative of 2 squared. 2 squared is 4, make it negative. And negative of 3 squared. 3 squared is 9, make it negative. So negative 4, negative 2, negative 4, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 4, and 3, negative 9. So my graph is going to look like this. So it does still have that U shape, but since there is a negative in front, it does cause all my y values to become negative. So that graph is now pointing downwards instead of upwards. Go ahead and take a moment to pause the video and try number 2 on your own. So when I graph this parabola, it still has the U shape, but it's a little bit different because we narrowed things out a tad. We're multiplying all of those y values by 2, which causes our graph just to get a little bit more narrow than it was before. Okay, I'm going to ask you again to go ahead and pause the video one more time and try these next 2 on your own. The only difference here is that we are adding 1 and subtracting 1, but the process of creating the chart and plotting points is still the same. So finding some points and graphing them, my graph looks something like this. So the last couple, if we look back, had a point, or what we call the vertex, on the origin. But this one was moved up 1 from the origin, and that is because of the +1 that we have added onto the end. When you create your graph for the second one, or your chart for the second one, I'm going to use the same numbers. When I put in a -2, I'm going to have 7. When I put in a -1, I'll have 1. 0, I'll have -1, 1, and 7, giving me a graph that looks something like this. Again, that U-shaped graph, but here, instead of being on the origin like the first 3 we did, origin, 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 instead of being on the origin, we have now moved down 1, and that is because of the -1 that we have after our x squared. So I would like to take a moment to check out what happens when we multiply x squared by a value. Here in this case, I'm multiplying x squared by 3 and by 1/3. And I want to see how those affect our graph. So the first thing we're going to do is we are going to graph y equals x squared. I'm actually going to do this one just in black so that we can compare the other two a little bit easier. So x and y, -2, -1, 0, 1, 2. I get 4, 1, 0, 1, 4. So -2, 4. -1, 1, 0, 0, 1, 1, 2, 4, and my graph is going to look something like this. Now my y equals 3x squared when I create my chart. I've got 12, 3, 0, 3, 12. So -2, 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It would be off my graph, but somewhere right about here. -1, 3. Still 0, 0. There's no addition or subtraction afterwards, so we're still at 0, 0. 1, 3, and 2. 2. This should be a 2. 2, 12, which is again off my graph. So my graph is going to look something like this. So notice it's a lot skinnier than my original graph was. And y equals 1/3 x squared. I'm going to pick numbers that I can easily divide by 3. So I'm going to pick -6, -3, 0, 3, and 6. And again, the reason I'm doing this is because I'm dividing by 3 after I square. So x squared is 36 divided by 3 is 12, 9 divided by 3 is 3, 0 divided by 3 is 0, 9 divided by 3 is 3, and 36 divided by 3 is 12. So I've got -6, 1, 2, 3, 4, 5, 6, and 12, which is again off my graph, so it'll be right about here. -3, 1, 2, 3, 0, 0, still because we don't have any addition or subtraction, 3, 3, and 6, 12, which is off my graph. So my graph looks something like that. So if I look at the original parent function, that black graph, I want to know, how does multiplying x squared by 3 change the shape of my graph? So when I multiplied by 3, I went from the black graph to the red graph. So the shape of the graph became more narrow. Or we can think of what actually happened is we took our fingers and grabbed these arrows on the black graph and just pulled them up and made our graph skinnier, and we created the red graph. So what we call that is a vertical stretch. Multiplying by 1/3, so I took the black graph now. When I multiplied 1/3, I got my blue graph. So that blue graph is more wide. Or we can think of taking our black graph and pushing it down and flattening it out to create the blue graph. So what we call that is a vertical compression. So it made it more wide or more flat. So we compressed it vertically. I've got 2 more I'd like for you to try out. Go ahead and take a moment to pause the video and try these on your own, remembering to fill in our blanks at the bottom about how those multipliers change the shape of your graph. So in my first graph, the only difference is that I multiplied x squared by -1. So when I look at the relationship between the black graph and the red graph, I see that the red graph just flipped over. What we call that is a vertical reflection. We just folded it over vertically from the top to the bottom. The second graph was not only a vertical reflection, but also we stretched it so that it became more narrow. So this will be a vertical reflection and a vertical stretch. And that brings us to the end of our video today. Thanks for watching.